the like lecture
So
time?
all the recorded video
Uh-huh.
with the permission of the speaker, if
Oh,
then it will be posted on the same website, like our TeaTalk website. There is a link to a
uh-huh.
YouTube channel.
Oh, okay, okay, okay. That's
Yeah.
good. That's good. Yeah.
So actually, in sense of the audience, roughly there are one third NTU students, one third NUS students from Singapore, and one
Okay.
third audience from other places, including other university in Singapore or overseas. So that's usually
Okay.
the thing. You can
And
see
is
some. Sorry.
it mostly grad students or undergrads or
That I
a
don't know.
mix?
For the few people I know, I think
Mhm.
they are graduate student, master
Mhm.
PhD level.
Okay.
But for people from NTU, I don't know. I can't see from by the username.
Yeah, makes
Okay.
sense.
Maybe I can provide you with some information about this participants from the NTU. So usually I will send all the seminar information to all the
Mhm.
PhD student and the research staff and probably also like faculty members. Yeah.
Mhm.
So I think most of the audience for NTU will be at least a postgraduate student. Yeah.
Okay.
Yeah.
I think it's already 5 past 10. Maybe we can get started.
Mhm.
Maybe I can
Good.
give a quick introduction to Hashay.
Mhm.
So, hi everyone. Thank you so much for coming to the talk today. First of all, happy Diwali to all our friends and students, colleagues from India. And today is Diwali. I think it's a festival of light in
Mhm.
India. And in theory, it's a public holiday in Singapore. Sorry to keep you working on a holiday. And
Mhm.
today it's our great honor to have Hashay Shah from MIT to talk about his work, how to manipulate editing behavior of machine learning models. So Hashay Shah is currently a PhD student in MIT. He's supervised by Alexander Manji. He focused on developing machine learning tools to understand and steer model behavior by targeting some intervention to learn algorithms, training data, and model to modify the model internals. So before we start, let's do some housekeeping. So there is a Q&A tab on your Zoom. If you're unfamiliar with Zoom, you can just ask your question there by typing in question. Alternatively, you can raise your hand. There is a raise your hand button on your Zoom. You click that, and appropriate time, um, if Hashay or I find this some time slot you can speak, I can open your mic. You can ask question directly, and and also there's a chat channel. You can ask you can miss me or other panelists for this talk. Yeah. Thank you so much for coming. Now I will pass the time to Hashay.
Cool. Thanks for the introduction. Yeah, I'll be talking about my recent work on decomposing and editing predictions by modeling model computation. This is joint work with Andrew Ilias and my advisor Alexander Madri. Um, So just to get some motivation, one of the main kind of motivators for building better models is that we want better performance, right? And usually when researchers think about performance, we think about state-of-the-art benchmarks, optimizing your hyperparameters, tinkering your ML pipeline, and so on iteratively. Um, and and this is great. Like we have benchmarks like ImageNet and now I don't know, Pile and so on, where we evaluate model performance. And we have had state of the art benchmark results and so on. But this is a bit tedious, right? There's usually a grad student involved, and um, it's not clear what exactly contributes to the state-of-the-art performance and so on. And as a result, what happens is that we often face this issue where these SOTA models can be brittle and lack robustness. So, for example, it has issues such as bias amplification, rare case issues like Tesla hitting a police car while using autopilot, or even it can pick up on shortcuts uh, that can cause the model to perform well on your data set, but not well when you deploy it. Um, So as a result, the core issue to me here is that we don't fully understand how these neural networks internally transform an example into a prediction, and that's the main issue that we are looking at in this paper. So just to set things up a bit, we view models as like any language model or vision model as a computation graph. And this computation graph takes as some example as input and then processes it with a computational graph and then outputs a model output. This model output can be anything like a cross entropy loss, correct class confidence margin, any metric that quantifies correctness, we call that f of z. Um, and typically, you can think of the edges in this computation graph as the components of the model. For example, in CNNs, these components can be convolutional filters across all the layers. In transformers, it can be attention heads and MLPs. Even in linear models, you can think of the individual weight coefficients as components, and so on. And the idea is that each edge is an independent component, and it contributes to an intermediate activation, which is then used to process the example and give you a final model prediction. Um, and so with this setup in mind, a high-level goal is to basically analyze how every component in the model across all layers, across all modules, kind of jointly turn examples into predictions. And again, this is high level, but I will kind of make this a bit more concrete in a bit. Um, so yeah, so just to give you some background, there has been a lot of work on analyzing model components, both in the vision setting and the language model setting. In the vision setting, people, have typically found out that when you look at the CNNs, um, the convolutional filters in the early layers learn to detect curves and frequency of analysis. More recently, there has been work that shows that, like, convolutional filters in deeper layers detect higher level concepts. So David Bauer's work in 2020 showed that if you look at the activation maps and then compare with those with segmentation maps, there's a high correlation between what the activation maps highlight and what the segmentation maps highlight. Um, and then more recently in the language model space, that or each MLP neuron characterizes in a transformer. So Olsen et al. Showed that there's some induction copying mechanism that is being learned by attention heads. And then Dye et al. Kind of focused on kind of localizing knowledge within neurons, MLP neurons in a transformer, and showed how this can be used for editing. And then more recent work in like mechanistic interpretability have kind of identified even more mechanisms, like specific mechanisms that can be understood by humans. Um, and the high level summary again here is that the work currently tries to reverse engineer or characterize specific model components. For example, they would look at a behavior of interest and then try to localize that to a few components and then try to study how these components are like executing this function. And in our case, the focus is a bit different in that the problem statement is that if I have some example F and an example Z, all I want to do is estimate how each model component contributes to the final model prediction. So the goal is not to understand whether a component is encoding some human understandable property, but just to know that if I have some example, what are the most important components in the model across all layers? What are the least important components? And the focus is more on this macro level property of how components impact predictions rather than the components themselves. And our approach to do this is basically we can predict how interventions to a subset of components changes the final prediction. Again, this is a bit technical, so I will break it down in a bit, but the goal is you can turn this problem into a supervised learning ML problem, and then use supervised learning to kind of infer how every component kind of contributes to the prediction. Um, Again, please stop me if you have any questions or anything. I'm happy to kind of answer them. through it. The first one is where we kind of define this framework of component attribution. Then I'll talk about a method to do component attribution at scale for like vision models as well as language models. And then I will focus on one application of component attribution, which is model editing. So if I have a model, how can I edit its behavior to kind of satisfy some property? Cool. So I'll talk about the first part of the work first, which is which is this component attribution framework, right? But before doing that, actually, let me just give you some brief background on what I mean by attributing model behavior in general. Like, if you forget about components for a second, what have people done what do people mean when they say attribute model behavior? So to show that's most or least important for a given prediction, right? And people have come up with various ways to do this, and they've shown that this can help enable model debugging in some cases. Um, and then there is more recently the work on data attributes. For the model to correctly predict this as an airplane. And it will also tell me which points are actually harming the prediction of this model on this airplane example. So you can think of this as an embedding over all the training data set examples. And again, recent work has shown that if you can learn a good data attribution method, you can use this to optimize your data set. Um, Cool. And this work, I'll talk about this component attribution problem, where the goal is to identify subsets of a model that are most or least important for prediction. So that what this means is that if I have a specific example Z, I want to know which components within a large scale model are useful or harmful for the prediction of this output of this example. And and the main application that I'm going to stress in this that I'm going to focus on in this talk is model editing. Cool. So with that out of the way, I'm now going to talk about component attribution and the key idea underlying this framework, and which is that if we can somehow understand how every component contributes to the prediction, this means that we should be able to estimate how these interventions change the prediction. So when people say understanding model behavior, it's a bit vague. And what we are saying is that we can actually think of this as a prediction problem, where if I change some components in my model, and if I understand how the model internals work, then I should be able to predict how this changes the prediction. Um, right. So you can think of this as a meta supervised learning problem. Um, Cool. So when I say interventions, what basically mean in in the context of this work is component ablations. So what I mean is if I have a model and if I have an input and an output, I can define an ablation in terms of a Boolean vector, where if the Boolean vector value is 1, that means that I'm going to ablate the model component, and if the Boolean vector value is 0, then I'm going to keep the model component as is, right? So if I have like C model components, then you can have 2 to the C possible different ablations to this. And so when I say intervention, what I do is I have some corresponding ablation vector. I apply this to the model and then see how the prediction changes when I do the ablation. So in this case, you might find that ablating like 2 random components might make the model less confident about this being a cat. Um, and again, one thing I want to stress in this talk is that the ablation method is a design choice. You can think of any ablation method that, there is no single optimal ablation method that works best, right? In this work, we kind of focus on, so we ablate components by simply zeroing out their parameters. But previous work in interpretability have also considered, adding Gaussian noise to the parameters of the components, or like reinitializing the model parameters and so on. Cool. So now that we know what component ablations are, I'm going to talk about like what does it mean to have a component attribution. And like I said, so the component attributions are basically estimators that, and you can think of these estimators as functions that take as input the ablation vector, and then they output how the model prediction would change if I applied this ablation, right? So again, the setup is I have some example Z, and I know that its prediction is f of Z. And what the component attribution of this example GZ should do is that it should take an ablation vector as input and then predict how the ablation will change the model output. Um, does this make sense? I guess this is an important thing to kind of understand. So I want to know for sure that this makes sense. Cool. Um, so yeah, so the you can once you so you can so the TLDR is a component attribution maps your ablation to a prediction for a given example, right? And then you can formalize it even further, and you can think of it as this approximation where if you have an example and a component ablation, your ground truth value here or your label here would be what would the actual ablated model predict. And the goal here is you want to somehow learn a component attribution function that takes this ablation vector as input and then predicts the ablated model's output. Right? So you all the thing in the gray box is what you already have, and the thing on the right, the G of V, that's the function that you want to learn, right? And we kind of focus on the simplest possible instantiation of this estimator, which is just a linear model. So in this case, what we are saying is that this linear model should should basically operate over the Boolean vector and then just output a prediction as a inner product of W and then B, right? So one way to think of this is that the attribution scores that you learn, the W vector, it signifies how each component contributes to the final prediction. Right, so you can think of Wi. If it's positive, that means that if I ablate this component, then my prediction or the estimated prediction will go down by this value. Or if it's negative, it means that if I ablate this component, then my prediction will go up by Wi. So you can think of these attribution scores as component-wise contributions of sorts, right? And again, this is just in the linear model setting. Like G of V can be a non-linear classifier as well. We just we just started with the most simplest setting, which is a linear model. Um, Cool. And so the goal of a component attribution is to be predictive in some sense, right? So what we want out of a component attribution is that if you sample a new ablation that it has not seen before, and then you correlate what the actual output of the updated model is, and then what the component attribution predicts, then this should have high correlation, right? So it should tell me which ablations impact the model prediction a lot and which ablations don't impact the model prediction a lot. And so the way we evaluate these component attributions is basically the Pearson correlation between the ground truth ablations and the attribution based estimates. And we want this to be high in large scale settings. Cool. So I'll now give you an example of what this looks like in practice. So let's say you have this ImageNet example Z. This can be an image of a cat. And then you have this trained model F. This can be a ResNet 50 classifier. And in this case, the set of all model components will be the set of all filters and all layers of the ResNet 50. So this turns out to be around 22,720, but this can be this is a function of the exact model architecture, so this can vary. But the thing I want to stress is that we are looking at all filters across all layers jointly, which makes this method kind of straightforward in some sense. So yeah, anyways, so once we have the setup, what we do is what we want is that for any component ablation we apply this ablation to the model. We evaluate the output of the updated model on this example, and then the goal is to have this be approximately equal to the component attributions estimate. Cool. So now I'll move on to the second part and talk about um, component attribution via regression, which is our general method for computing these attributions. Um, and like I said briefly before, we can now think of this component attribution method as a supervised learning problem. In the first step, what you want to do is you want to make a data set of component ablations. So for every example, you can do three things. You first generate a large number of random ablation vectors from some fixed distribution. So these random ablation vectors might, ablate 5% of all components at any given time. And once you have this large database of ablation vectors, you can ablate the model using these vectors and then log the effect on the model output. So this is um, so what you would get is a data set of the ablation and the effect of the ablation on the model output. And then once you have this data set, you can just think of uh, learning a good component attribution as a linear regression problem, right? Where so in green you have this data set of component ablations from the previous slide. In red is what the ground truth output of the blue thing is what we want to learn, right? It's the component attribution if you think of the attribution as an estimate, where the W encodes the contribution of every component and the B is just the bias term. So yeah, the hope is that the fitted weights of this linear model are actually predictive in kind of are predictive of the ground truth output of the updated model, right? Um, yeah. Any questions so far? Okay, so there's a question. Yes. Is recent work on extracting latent knowledge related to component attribution? Yeah, it is kind of related at a high level. I'll briefly talk about this when I talk about the applications to model editing, because you can think of extracting latent knowledge as some sort of editing task. But I'll get to this later. Cool. Um, so okay, so now that we know, like, okay, there's this linear regression problem that you can optimize and get the component attributions. How would you evaluate this? Again, so what you can do is like you can take the same setup as before, and then see what the correlation looks like at the example level. So over here on the y-axis, I have the estimated core attributions model output. On the y-axis, on the x-axis, I have the true counterfactuals for this example. And what this plot tells us is that the attributions learned using this method are actually predictive of the final model output under interventions, right? So what this tells us is that even for ImageNet scale models and for image classification tasks, a linear component attribution is pretty effective at capturing this model behavior accurately. And you can also look at this at the dataset level. And what this means is that you recompute this, but for every example in your ImageNet validation set, and then you look at the average correlation. And what we find is that our method works significantly better than what people typically use in practice, which is like leave one out, uh, and like this gradient-based approach called gradient times parameter, and some other approaches that try to quantify the importance of component level attributions. Um, and so what this plot tells us is that if you just ablate components one by one, which is the leave one out method, that's not a good way to measure the importance of a component in the model, because the component also depends on the interactions on other between other components across layers and so on. So what you really want to do is ablate multiple things at a time and then frame it as a linear regression problem to get better performance at this task. Cool. So this kind of concludes the okay, actually, yeah. So in our paper, we kind of show similar results on language models too. So Llama 7B, 70, Llama 270B, and we also like tinker with the architecture. So we look at MLPs, CNNs, transformers, and so on. and linear component attributions work consistently well. Um, Again, like for large scale models, it may be a bit inefficient right now to kind of estimate these attributions, but I'll talk about scaling this up later. Cool. And okay, I see some more questions. One sec.
Yeah, so two more questions about the model function.
What variable is the correlation computed for? Yeah, so the variable, I briefly talked about this in the beginning. So when I say f of z, it can be any variable that quantifies model correctness. So it can be like the loss, but it can also be like the confidence of your examples if you don't have labels, or it can be the margin. It really does not matter that much. But yeah, for now, you can think of this as the loss. Yeah, cool. Um, so moving on. So
Sorry, Hachi. I think there is also another question, the second question. Yeah. So the question is, I understand how the model functions, but I'm struggling to understand how I would implement in a workflow for refining my model and dataset. So could I trust you to provide
yeah,
example? Yeah.
I'm not sure what you mean by refining my model and data sets. Maybe model editing is one way to refine the model. Uh, but yeah, if you can clarify what you mean by refining the
I think the audience is a bit confused about the workflow or the
okay.
steps
There's a
constructing.
see. Yeah, I think after finishing the talk. Um, there's one question. How many components in a Llama 70B and how many random ablations do you generate? Um, each MLP neuron as a component in the 70B model, then there are around like more than 500,000, roughly 500,000 components. Um, and so if you think of the number of components as the number of dimensions in your linear regression problem, your random ablations need to scale linearly, which means that I also need to generate around 500,000 ablations to get a good model, to get a predictive attribution score. And this is like one of the major limitations of this approach right now, which is that the number of samples or ablations you needs scales with the number of components. So coming up with faster ways to do attribution would be nice. Yeah.
Yeah, well, I remember there are some people doing combinatorial space search. So those kind of methods applicable to solve this problem of scalability here.
Yeah, I think anything combinatorial would be difficult to scale. I think using gradients in some way to kind of warm start the linear regression would be a great way to kind of speed this up. And seems very doable to me. Yeah.
I see.
Okay, there's one more question. As I'm understanding correctly, yeah, okay. So this person is asking if the ablation is done at the weight matrix level or the block level. So again, it really depends. It depends on how you partition the model into components. So if you partition the components into like individual parameters, then it will be weight level. But if you partition it into filters, which is what we do, then each component would correspond to a subset of parameters or like a block of parameters. You can also think of doing this at the layer level. Things get a little tricky because the ablations might be too aggressive at the layer level, if that makes sense. Um, cool. So moving on, I'm going to talk about the main application that we look at in this paper, which is using component attributions to edit models. Um, So I'll start with a quick summary of what I mean by model editing because it's somewhat of a vague notion. Some people mean different things when they say model editing. But the setup that I have in mind is that you have a few target examples from some distribution, and then you have a few reference examples from a different distribution called dereference, and then you have some model F that you want to edit. Um, And so the goal of model editing is that you want to update this model to change your model outputs in some desirable way on the target distribution, but then you do not want to alter the model outputs on the reference distribution. Um, and so that's the high level goal of editing. Um, and when I say alter model outputs, it can be like improving model performance on the target distribution, but it can also be something like unlearning the specific latent knowledge in the language model, like someone asked. So if the goal is to unlearn, then you would want to nullify or like change the model output to be as good as a random classifier on the target distribution without altering its general capabilities. Right. Can I see one more question? Can we use the partial derivatives to estimate the attribution instead? So yeah, so we use this as a baseline. So the gradient times parameter baseline is essentially a Taylor approximation that uses partial derivatives to compute the attribution scores. And as you can see, this does not work very well. Um, and the main reason is that gradients are not good at estimating um, large changes in parameter space. Um, so, so yeah, that's the main issue. That's the main reason why gradients don't work well here. Can it also be qualitative aspects of preferences instead of performance? Uh, I guess for now we don't have a framework that accounts for like qualitative aspects. But I guess if you can have a proxy metric for the qualitative aspect, then you could cast it as a attribution problem. But we don't directly support preferences right now. Cool.
Hey, Harshan, sorry. Yeah, I think you probably missed one question from Apan. Yeah.
I
So,
I think I answered that one as well, the 70B one. Yeah.
oh, okay. I see. Yeah. Okay.
Cool. So going back to the model editing application, the reason why component attributions are a good fit for this problem is because it essentially flips the question, right? So in component attribution, the question is how would model outputs change if we were to ablate a subset of components? Whereas in editing, the question is which components, when ablated, would change model outputs in a specific way. So the main idea here that we have is we can use attributions to identify model components that change model behavior in some way because attributions predict model outputs. So you can use this as a proxy to optimize and like kind of hone in on the right components that will change the predictions in the right way. Because otherwise, it's a combinatorial problem, which we are kind of sidestepping by using attributions as a proxy for the actual model ablations. And the nice thing about this approach is that you don't need to do any additional training. You just need to ablate the right components to edit the model. And the second thing is that it's pretty sample efficient, which means that you can just use a few examples from the target and the reference distribution to kind of make this edit. So the method that we come up with is called core edit. And essentially what this does is that if, let's say before model editing, my performance on the target domain is 60%, and on the reference domain, it's like 80%. What core edit does is it takes a few target and reference examples as input, and then outputs a targeted ablation called V. And if I apply this ablation to the model, uh, the ideal scenario is that the target accuracy increases to 85%, but the reference accuracy does not degrade at all. This is what we call a model edit, where we use some examples to identify the right ablation and then apply the ablation. Um, cool. So our method has 3 steps to it. I'll just break it down slowly. So the first one is you use our method to compute the attributions for target and reference examples. Then in the second step, what we want to do is we want to somehow quantify which components are very important or not important at all for the target distribution, but not for the reference distribution, right? So if the goal is to optimize performance on the target examples, you want to identify components that are significantly more important to the target distribution than to the reference distribution. And we do this via hypothesis testing. It's a standard hypothesis testing problem. So you apply a hypothesis test over the distributions for every component, and then you use the statistic to kind of infer the right the right components. And I'm going to skip the details of the testing for now, but you can check the paper for more for the exact method. And so in step two, once we do this relative importance scoring, and using these scores, we can then ablate the components that most negatively impact target predictions, right? So if you use these test statistics to ablate the bottom key components with the lowest test statistics, what that means is that if the component attributions are predictive, it should improve model performance on the target examples without impacting your reference examples. Yeah, so again, just to backtrack a bit, the high level idea is that you want to somehow compare the attributions of target examples and reference examples to then identify which components are the most important for the target examples. And we do this comparison with hypothesis testing. That's pretty much it. Cool. Now I'll kind of talk about some applications of this editing method. So we look at 5 applications in the paper, but for this talk, I'll just focus on the last 3. And I'll start with the first one, which is like improving group robustness. So in this case study, it's a well-known problem in computer vision where models kind of latch on to these shortcuts or spurious correlations in biased training data sets. And then at test time, if you remove the spurious correlation, then your model performance degrades significantly, right? So 2 standard benchmarks that people use in this for this case study is like Waterbirds and Cerebay. And in both cases, so in Waterbirds, what you have is that you have waterbirds on water background and then land birds on land background in your training data. But on your test data, you only see waterbirds on land background. So you have so if a model relies on the background to predict the bird, then it's going to perform very poorly on the test data. And then similarly in Celebi, there's some spurious correlation between color, between your hair color and the gender. And so if you just run ERM on like a ResNet 50, all of these image pre-trained models kind of latch onto these spurious correlations. And it, as a result, performs pretty poorly on the minority groups in your test data. Okay, so in this setup, what if we apply core edit in 2 steps? So first is you need to collect some labeled examples from both the minority group and the majority group, and this can be as few as 10. So yeah, as someone just asked, you do need labels on the target samples. But you only need a few examples. So that's the advantage of an editing method. And the reference examples will be from the majority group, which you already have. And what we found is that if we apply core edit to identify the right components and then ablate those, we see that, so on the x-axis, we have the number of model components ablated, and on the y-axis, we have the test accuracy. And so what we see is that the worst group subpopulation, which is typically the group where the spurious correlation and the true label conflict. So you can improve your performance on the worst group by 25 to 40%, depending on the data set, by just zeroing out the right parameters or the right components. And so what this is saying is
There's
that,
a question who raised hands by Xuan.
okay, what's the question?
Yeah, so
Oh,
Chen Xuan, could you unmute yourself and raise your question? Chen
Yeah.
Xuan.
Sorry, I don't have any question. Sorry.
Okay.
Oh, okay.
Oh, it's a mistake. Okay, good. Yeah.
Cool. So again, going back to this case study, what I want to say is that simply zeroing out the right subset of components can significantly improve your performance on the worst performing subpopulation without impacting your overall train and test accuracy. And this is somewhat surprising to me because in a typical ResNet 50, there are thousands of components, right? In the ResNet 50 that I just discussed, there's like 20,000 components. But then if you can edit and just zero out around 20 to or like 200 components, you are significantly improving performance on some subpopulations. So that was somewhat surprising to me.
So I actually I have a question about this. So you are zeroing out a component according to the target examples. Am I right?
I am zeroing out components using this three-step approach. So I'm using the target examples and the reference examples
Okay,
to identify components that are very important for the target examples, but not important for the reference examples.
I see.
And then I'm updating that subset.
I see. I see. I get it. I get it.
Because if you don't do this, it's possible that the components you update are important for all distributions, not just for the target distribution. So you need some way to adjust and localize the right components with a reference distribution. Cool. I'll also talk about another case study which involves zero-shot clip classifiers. So clip classifiers are basically a nice way to kind of um, define your image classification task on the fly because it does not require labels when you train it. Um, so people have been using clip classifiers for fine tuning purposes or for like zero shot purposes a lot these days. And one issue with clip classifiers is that it's very sensitive to typographic attacks. So what that means is that if I have a image of books, it will correctly predict it as books. But then if I place a sticky called Twitter with the word Twitter in it, then it's going to change its prediction to Twitter. And this is an artifact of how it's trained with contrastive learning. Um, and this makes it susceptible to typographic attacks in practice, right? Someone can easily just have a sticky or something that says something that you don't want the model to output. And the editing setup, the editing experiment here is that if I have some target examples with the typographic attacks, and then if I have some reference examples without the typographic attacks, can I use attributions to localize the components that are responsible for this failure mode, right? And again, the way we set this up is that we use these examples and basically compute their attribution scores and then identify components that are very important for the typographic attack ones, but not for these ones. And then we show that as you ablate the most relevant components, your overall accuracy remains at 95%, but your accuracy on these examples with the attack increases as you ablate more components. And this is really cool because again, this is saying is that you can downweight some capabilities or some spurious correlations in your model by simply zeroing out the right parameters. Um, and I guess I'll end with one last case study, which is on localizing backdoor attacks. Uh, there's a question. Yeah, so again, it can be a little uh, prone to overfitting. So if I just have, I don't know, like two examples for the target data and for the reference data, it's possible that the attributions um, it's possible that the attributions are somewhat sensitive to these examples and it's not capturing the distribution wide property. But the nice thing about attributions is that instead of like exploring things in the parameter space, you are exploring in this lower dimensional attribution space, component space. So it's a little less prone to overfitting. So even with 10 examples, we could do editing that works pretty well. But yeah, as you have more samples, your method will perform better. So more examples always help. Um, I guess the other question is if the target and reference distribution is already available, is choosing the right examples for step one. Oh, that's a good question. Yeah, we haven't looked at this. We just look at we just take a random set of 10 examples from the training set and then we do the editing experiment. But it is possible that if you can like curate your editing set in a more smarter, like in a clever way, then you will have better editing results. That's a cool question though. Yeah. Yeah. But for what it's worth, even if you have even if you randomly sample like 10 to 20 images, it does work pretty well. And the variance is not too much depending on the sampling. Cool. So the last case study is on localizing backdoor attacks. So here the setup is that you have, let's say you're pre-training, well, not pre-training, but let's say you're training a model, but you don't have access to your training data set. So an adversary can plant a blue square that always appears in half of the airplane images, for example. And what happens when you do this is that the model learns to rely on the blue square to predict airplanes. And so whenever so in the third row, if you have a frog with a blue square, the model will predict it as airplanes because of the spurious correlation that has been adversarially planted in the training data. And again, so if we apply this core editing method to this problem, we can localize and identify model components that if ablated, um, it makes the model more robust to these blue squares, but does not degrade the overall test accuracy that much. And in this case, because the feature is very well defined, you can actually look at which components you have ablated. And if you look at the filters and their activations, you see that the components that you ablate only kind of rely or like only highlight the blue spurious correlation. So this is a nice qualitative way of just checking what exactly is what exactly is this editing doing in some sense. Cool. So I'll just spend 2 minutes on discussing some future work ideas that I've been thinking about. I'll first talk about improving the method itself. So like someone mentioned, the attribution method can be slow if you have a lot of components in your model. So coming up with faster component attribution methods for language models is a big is a major future direction. Um, Even coming up with better nonlinear attributions that predict the model output better, for example, decision trees or like kernel methods. I think that could be a nice a nice improvement because that would directly improve your editing results too if you have a better attribution model. And the last thing is finer grained model editing. Right now, I'm simply zeroing out the most important parameters, but maybe the right way to do this in a more practical setting is to do some localized SGD or like localized gradient updates, where you first localize which are the most important components, and then you update those components via SGD or something like that. Um, and from the applications front, I'm kind of really interested in three applications. One is, can we use these attributions to kind of discover model dependent subpopulations? So let's say we don't have you don't have the labels of the examples, but you know what the model outputs are. Can you somehow identify which examples rely on the same components? And can you use this to like edit subpopulation level components in an unsupervised way? Um, the second idea is to detect adversarial inputs. So in language models these days, there's a lot of attempt to like jailbreak, um, like have some prompt injection attacks and so on. And if and the idea is that if your adversarial attack does impact model outputs in a substantial way, then it should have very different attributions from a natural example. So these would show up as anomalies in your attribution space. And so you can maybe flag adversarial examples by running outlier detection method on attributions. Um, and the third example, the third application that I'm super interested in is a bit more sciencey, but it's basically understanding how these predictions change over time. So if I have a image of a cat, how are these attributions kind of how is the model prediction being refined over training epochs? Are the attribution of the first layer first kind of stabilizing and then being used for the second layer attributions, or like how exactly does this happen? And is it consistent across examples? So all of these questions are um, can be like directly tested with attributions, I think. So yeah, these are the three applications I have in mind. Um, and yeah, that's about it. So a quick summary. Like there are two main things. One is if you want to identify how each component attribute contributes to a given example's prediction, then you can use a method like code to do this. And then once you have these attributions, you can you can basically edit model behavior at the example level or more vaguely at the subpopulation level using this editing framework that I just discussed. Cool. Yeah, any questions?
There is one more question in the Q&A tab.
Has yeah, we haven't looked at medical applications. Um, we mostly looked at the standard image classification settings and we explored some language modeling kind of problems, but we haven't really looked into these kind of problems of short-term mortality and so on. Yeah.
Any more questions from the audience and from Yong? Do you have any other question?
Yes, I do have maybe two questions. Yeah, so
Yeah.
actually, I really enjoy talk. It's quite interesting and inspiring. So even though I'm not really working on this direction. Yeah.
Mhm.
So my first question is, I definitely understand the how to say the three steps in the core editing, and
Yeah.
your third step is that you will try to apply the components that actively impact the target predictions, right? So I just have a rough idea in my mind is that instead of like just removing or updating the elective components, I'm just wondering if it does it make sense to you that if it's possible for us to maybe enhance the importance of those kind of components that are like a positivity or how to say important for the final predictions. For example, in one of the case you mentioned that sometimes the model may misclassify frog as plane because of the distance of the background, like the blue sky, right? This is actually a very interesting example. So I think for these kind of models, if we can, for example, force the model to focus on or pay enhance the importance of the components that are more associated with for example, the area of the frog, it may
Mhm.
also like resolve this kind of issue, right? I'm just wondering, does it make sense to you? Is it a possible way to make use of your approach to enhance the model performance?
Um, it, I think model attributions, component attributions are good if you want to if you want to downweight a feature that is harming a prediction. If you want to learn a new feature from scratch, that would involve more training or more data, I think. So
Okay.
so for example, in the first case study where we improve a performance on the subpopulation, it's because we are downweighting a spurious correlation that it's relying on. Like in this case, it's not because uh, editing is learning a new feature per se, but it's more about like downweighting a bad feature that's making it not robust. I'm
Hmm.
not sure if editing methods right now in general, not just core, are good at learning new features, if or like enhancing model performance from without any new data. I think
I
for
see.
that, I think just fine tuning on more data would be the most effective thing. Maybe on the right data would be most effective. Um, Editing is nice if you want to unlearn something or like downweight a spurious correlation or um, adjusts class level performances and so on.
Mhm.
But if you want to just improve performance from scratch, that seems unlikely, I think, with just editing. Um,
I see. I see. I got it. Yeah.
like you can upweight, but you're basically upweighting by implicitly like downweighting the negative components. So it's not really like learning anything new, I would say. Just like more of adjusting and steering the existing features that the model has.
Mhm. Yeah, I see. Yeah, this is just some random thought in my mind. Yeah, because when you talk about these kind of examples, I'm just wondering, like, for example, in some situation, like take the classification of for example, images of dogs and images of wolves, because the image of dogs and image of wolves they share some similarity, right? I think if we train
Yeah,
model, definitely the model will learn those kind of features that are commonly shared by the image of dogs and image of wolf, but there definitely are some other features that can distinguish wolf from dogs, right?
yeah,
So if you want to improve the model performance for this kind of classification task, definitely we need to improve the importance of those kind of features that distinguish these two types of animals. So I think your approach is quite good. for example, it's very feasible, very easy for us to unlearn or update the
Right.
components that like impact the prediction. But yeah, I'm just quite curious about if you can do the other way around.
Yeah, I'm not sure, to be honest. I think my first guess would be to just train or fine-tune the data, or fine-tune the model on
Oh yeah,
more volumes of tokens than do this. I think that seems like a simpler approach, but there's maybe something here. Yeah, I'll need to think a bit more about this.
yeah, yeah. Yeah. I think so, Tim, I'm not sure if we still have time for one more question. Actually, I do have one question.
I
Yeah.
think there's a question from the audience.
Oh, okay. Yeah.
Actually, quite a few.
Oh, okay. Sorry. Yeah. I'm not checking. Maybe we can take the question from the audience. Yeah. Sorry.
Okay, so I'll start with the first one. Ablation behavior is not predictable. My mean. Yeah, I guess you could think of using this to like prune the model, but and then as a result reduce computation by ablating the components that are not contributing to the prediction. But um, I guess if I'm reading the question correctly, the issue is that different examples rely on different components. So having a common prunable subset would be unlikely, I think. So you're better off like with the standard pruning methods that people have been using. Um, yeah, so the data attribution paper that I was mentioning is called data models. Um, yeah, it's called data models predicting uh, predictions from training data or something like that. So that's the title. Um, do you think model editing is effective in steering LLMs compared to prompting on fine-tuning? Yeah, I do think so because I guess in when you do prompting, you need to somehow specify or like manually convert a task and specify that as a prompt. And there are cases where you may not be able to do this, but I guess you have more expressive power when you kind of on the components. I'm not fully sure if this is better than like context distillation, but there was this recent paper by Anthropic. It's called feature steering, where they evaluate whether uh, like these activation steering methods and so on are better than prompting or just fine tuning. Um, I think the main difference is that if you don't have enough data, then you should edit. If you have a lot of data that it makes sense, then I think fine tuning might be the right way to go. Um, yeah.
I have to leave for a meeting, but please continue. Thank you so much, Hashem, for the nice talk.
Yeah,
Okay, let's
sure.
keep in touch. Bye bye.
Cool. Bye. See you.